So let's say let's just drop my physics book again, 2 kilograms, initial velocity of 0, and ask how fast is it going when it gets to the ground at a height 30 meters from the top of the building. 30 meters from the top of the building. And we've done this with kinematics, but let's go ahead and do it with the work energy theorem. Let's draw a free body diagram of the book as it's dropping. The force down is the gravitational force. Ooh, there are no other forces. So the work done, the total work done, is just the work done by gravity. And the work done by gravity is the work, oops, sorry, I'm getting ahead of myself here. Total work done is the work done by gravity, and we know that the total work done, which is the work done by gravity, is equal to the change in kinetic energy, 1/2 mv final squared minus 1/2 mv initial squared. So we just need to figure out the work done by gravity from the definition of the work. Work done by gravity is the magnitude of the gravitational force, mg, times the magnitude of the displacement, 30 meters, times the cosine of the angle between them. We never drew the displacement vector, right? The gravitational force vector is in that direction, and the displacement vector is in that direction. Those two vectors point in the same direction, so therefore the angle between them is 0. And so we already knew this, that the work done by gravity is mgh, where h is the downward displacement. So I'm actually not going to go ahead and plug those numbers in, but just note where h is 30 meters. H is 30 meters. We could have called it mgd, where d is 30 meters, but we tend to call it mgh. And so mgh is 1/2 mv final squared minus 1/2 mv initial squared, because I'm going to go ahead and plug that in. And so therefore, we can cancel the m's. That's why you don't want to plug your numbers in first. We can cancel the m's, and we get that, oh, and not only that, but the initial velocity is 0, so we can cancel this all together. And so we get gh equals 1/2 v final squared, and so therefore v final is the square root of 2gh. Turns out that that is true for any free-falling object that falls from rest through a height h, but that's a specific case for a free-falling object that is only under the influence of gravity that falls through height h. It's actually a little less specific than we think, because let me look at a different example. I'm going to do example 2. Don't draw on your same example, but I'm just going to illustrate. Instead of sending the book off the top of the building like that, let's pretend that I set up a slide, or it could be like construction workers have these ways of getting rid of their waste by putting these sort of tubes. So we can set up a slide and have this thing slide to the ground. I'm actually going to set up a slide which is not even straight. Let me take that back. We'll do the not straight slide third. Second, let's do a straight slide. So part B, we're going to do a straight slide, which has an angle theta. We've already done something like this, but let's go ahead and repeat it. So I'm going to take the building of height h and put a slide and angle theta, and we're going to slide the book down that slide. So here we go, and again, h, the height of the building, is 30 meters. Okay, so this is the same problem, but instead I'm dropping the book straight down, I'm sliding it down, and I want to know what's the speed of the book at the bottom. Well, I'm going to again do it from the work total equals change in kinetic energy, and I'm going to write it out again, minus 1/2 mv initial squared. Whoops. But now, what is the work total? Well, now, in order to figure out the work total, we really still want to draw free body diagrams. We don't have to solve Newton's second law, but we want to draw a free body diagram to make sure we're taking into account all the work done by all the forces. So we draw a free body diagram of this book, and we find that it's got a gravitational force in the downward direction. It's got a normal force perpendicular to the slide, and it is frictionless because I didn't say take into account friction. And those are all the forces. So we can say, work total is therefore the work done by the normal force plus the work done by the gravitational force equals 1/2 mv final squared minus 1/2 mv initial squared. Okay, so we got to figure out these two things. So let's start with, I don't know, the work done by the normal force. Let's calculate that separately, right, from the definition of work. The work done by the normal force is the magnitude of the normal force times the displacement times the cosine of the angle between the normal force and displacement. But now wait, what's the displacement? Well, the displacement, right, it starts here and it finishes here. So the displacement vector is that one, d. That's my displacement vector. And so what is d? The magnitude of d is, but wait. We're going to need to know it. If I know h, d, and h, we can do some geometry, right? Don't worry about what numbers we know and what numbers we don't know. We can look at these relationships and we can still do SOHCAHTOA, sine theta, cosine theta, tan theta, and see if one of them gives us the relationship between h and d. And indeed, sine theta does. It is opposite h over hypotenuse. The h is the height here, not the hypotenuse. H over d. So therefore, h equals d sine theta. The height of the building equals the path length, the displacement, times sine theta. That's just geometry. Nothing physicsy here at all. It's just geometry of the right triangle. And so since we knew what h was, again, I'm not worried about what we know and what we don't know, but for those of you who really always pay attention to what we know and what we don't know, so we know what h is, so we can write d in terms of a known quantity. D is h. So the work done, I should have written, the work done by the normal force is the magnitude of the normal force times d, which is h over sine theta, times cosine theta. Okay? Totally made an error. Did you catch the error that I made? Bad error, right? But I'm going to leave it. I'm not going to erase it because it's so important. And I've said it before. This is not the angle of the ramp. That is the angle between the n and the d vector. It is not the angle of the ramp. This angle is not the same as that angle. This angle is the angle between the normal force and the displacement vector. I guess I was just calling it n instead of f sub n. There it is, f sub n. And what is, so I should have written, here's what I should have written. Got to differentiate between the angle of the ramp and the angle in the work. The angle in the work is the angle between the two vectors. And just in case this is throwing anybody off, I'm going to replace n with f sub n because that is just the normal force. F sub n. This is the work done by the normal force. So I'm going to just give it a different Greek letter, phi, and phi is the angle between those two vectors. What is the angle phi? Well, look at the ramp. The normal force goes in that direction, and the displacement goes in that direction. What is the angle at any time between the displacement and the normal force? The angle phi is 90 degrees. Phi is 90 degrees. And therefore, the cosine phi is the cosine of 90 degrees, which is 0. So therefore, I didn't have to do any of this work because the work done by the normal force is 0. But you knew that because remember, the work done by a force, the force has to have moved the body. And the normal force in this case does not move the body. You do a real quick aside and say, does the normal force ever do work? If you're sliding a box across the floor, the normal force doesn't do work because it's not moving the body. But does the normal force ever do work, right? Aside, does the normal force ever do work? Which is not in the case where you're pushing something across a floor, but indeed it can do work, right? So the normal force does work when the body moves in the direction of the force. So if I therefore pick up this body from the floor, does the normal force do work? The answer is still no, because the normal force didn't make the body move off the floor. It didn't, right? As soon as you pick it up off the floor, there is no normal force, right? But what if instead I take the floor, I put the box on it, and I move the entire floor up like an elevator, right? Like an elevator. Or simply like, actually I have in front of me, you can't see it, but I have a can of soda on a coaster. So I move up, and the coaster, just like you see in the picture, the coaster is exerting a normal force on the can, and it does work because in that case, the normal, so if the whole thing moves up, then the normal force Fn and the displacement d, so therefore the normal force can do work. Yes, the normal force can do work. If you're in an elevator, what does work on you to move you upwards is the normal force of the floor. Okay, back to this problem. We want to know the speed of the book at the bottom of the ramp. We just figured out, the normal force does no work. It never does any work when you're sliding on a surface. It only does work if the surface itself is moving. Okay, what about the work done by gravity? Well, the work done by gravity, I'm just going to do it in the corner here. The work done by gravity is the magnitude of the gravitational force times the magnitude of displacement, which we already figured out is h over sine theta, times the cosine of the angle between the gravitational force. I don't even know what to call it. It's yet another angle. I'm going to call it smiley face. Angle smiley face. Angle smiley face is the angle between the gravitational force, mg, and the displacement, d. This is the angle smiley face. Can't really see it, but that's the angle we're talking about. Between mg and d. mg is straight down, d is there. So what is that angle? Back at our original picture, it is not that angle, but it is that angle, because the gravitational force points in that direction and the displacement points in that direction. So it is this angle here. This is the angle smiley face. And so it's 90 minus theta. That's the geometry of your right triangle. It's 90 minus theta. Wg equals the magnitude of the force, h over sine theta, times the cosine of 90 minus theta. Now everything is known and we can do the math, but go ahead and plug cosine 90 minus theta into your calculator and sine of theta into your calculator, and you realize that the sine of 90 minus theta is equal, the cosine of 90 minus theta is equal to the sine of theta. So without plugging anything in, don't forget that the work done by gravity is always mgh. We already proved this. I'm just doing it again. It was a trick, right? We proved that the work done by gravity, no matter how you get there, no matter how you get from the top to the bottom, the work done by gravity is dependent only on the displacement in the downward direction, h. The work done by gravity is always mgh. So you can use the definition of work to figure out the work every time, but it's every time going to end up equaling mgh, where h is the vertical displacement in the downward direction. In other words, work done by gravity is positive if you move down, and it's negative if you move up, because gravity is trying to slow you down. But it's always got a magnitude of mgh. Therefore, remember where we were, and we've done a lot of asides here, but remember where we were trying to find the speed of the book at the bottom, and we simply wrote down the work energy theorem, and it would have been really easy to say, obviously the work done by the normal force is 0 because the normal force doesn't move it. The work done by gravity is mgh because the work done by gravity is always mgh. We never had to do any of the rest of the work. Do you get that? Like, we could have just jumped right there and recognized that if we understand those concepts of what it means to do work and what it means for gravity to do work. So what we end up getting, and since also the initial velocity is 0, that one is 0, what we end up getting is, therefore, mgh is 1/2 mv final squared, and therefore v final, lo and behold, is square root of 2gh. The velocity, the speed of the book at the bottom of the ramp is the same as the speed of the book when we dropped it straight down. If it's only under the influence of gravity, and in the case of the ramp, it's under the influence of the normal force, but the normal force does no work. So if gravity is the only thing that does work, it doesn't matter how it gets there. If it goes down a height h, it's got a speed of the square root of 2gh. Before we leave this, I want to make a point here. I guess I was gonna do one more example, but this example is now going to be super easy. Let's put the thing on a curved slide. Still goes down a height h, and it makes it to the bottom. And we want to know what's the speed at the bottom. The speed we can do work total equals change in kinetic energy, and we can write down that far, right? Recognizing, drawing a free body diagram of the book at any point is got a normal force in that direction and a gravitational force in that direction. Normal force is always perpendicular to the slide. And then you say, But now the slide's curved. What does that change? Well, just think about it. We already made this statement, but I'm going to make it again. At any point, the book is here. The normal force is there. What is the direction of the displacement at that point? It is tangential to the slide. What's the angle? 90 degrees. What's the normal force here? The normal force is straight up. The displacement is in that direction. Right? At any point. Now, while the direction of the normal force and the displacement is changing as we go, the direction of each of those is changing, the angle between them doesn't change. Because the floor or the slide is not pushing the object. The object is always moving perpendicular to the, parallel to the surface. Even if it's a curved surface, on a slide, you're moving parallel to the surface. Normal force does no work. The normal force does no work unless the surface itself is moving. Does that make sense? So we already showed that. And so even in this case, the normal force does no work, 0. We don't have to prove it. We know that it does no work because the normal force is always perpendicular to the displacement. The work done by gravity is still mgh because work done by gravity is always mgh, where h is the displacement in the downward direction. And so therefore, because the initial velocity is 0, therefore v final is the square root of 2gh. Oh, surprise, surprise, surprise. Same thing. Doesn't matter how we get there. Okay, so you might have heard my chair squeaking, I'm not sure, but I realized it was squeaking while I was talking. So there is one more point I need to make here, and that is something special about the work done by gravity, right? Something special about the work done by gravity. I just stressed to you that the work done by gravity is always mgh, where h is the displacement in the downward direction. Or you can think of it as it's always got a magnitude of mgh, where h is the vertical displacement. And gravity does positive work if you move down, and gravity does negative work if you move up. Okay, because gravity is trying to speed you up as in the downward direction, it's trying to slow you down in the upward direction. Okay, but the fact is that if I start here and I end up here, unless, building or anything, doesn't matter what it is. If I start there and I end up there, and let's say that through some kind of machinations, my book does this, and does this, and does this, and does this. Maybe it's got a jet engine on it, right? But it still ends up there, which is a height h below where it started. Following that red path, what is the work done by gravity? The work done by the gravitational force is still mgh. And the work done by the jet engine that was attached to the book is something other than mgh. But the work done by the gravitational force is still mgh. If it starts here and it ends here, it doesn't matter how it got there. The work done by gravity is mgh. And if it starts at the bottom and it goes to the top, then the work done by gravity is minus mgh. But it's still always the same value, no matter what path it follows. That is a special property of this kind of force. It's called a conservative force. It's called a conservative force. Gravity is a conservative force. It says that the work done is path independent. Work done is path independent. The work done between the initial point and the final point, doesn't matter how you got there, initial and final, is path independent. Now, is there such a thing as a non-conservative force?